All right, so your assignment number 3 has been released. Guys, I know the most urgent thing for you to get prepared will be your written test next Thursday. However, don't forget your programming test number 2 is also approaching. That one there naturally will be more challenging than your programming test 1. That's going to cover exactly what assignment 3 is going to help you learn. So I would really suggest you try to get started right away. Right? It does require another level up of understanding about recursion, link structure, etc. So you really want to get started and get your hands on with that right away. My office hour open there. As usual, just come to me if you got any trouble, right? I cannot emphasize enough for assignment number 3. Plan your time. And your written test that's going to happen next Thursday, the same location. You can look at the guide. I will try to make some example questions for you by the end of tomorrow, so you can definitely try them out. And then I'll reach out to you about some review session there, optional over Zoom, if you want to ask me questions. I'll reach out about the detail very soon. And the makeup lecture for your programming test 1 on the ADT stacks, it will be covered in the written test. So if you haven't caught up yet, you really want to do it soon. And lecture note template, office hour, TA content, all the same. All right. Questions about the course? All right, let's now do the recap from last time. So last time we basically continued with the topic about trees, of course. That will be the main topic for the rest of the term. And we'll talk about recursive definition for trees. And this is the kind of recurring pattern that you will see for your assignment number 3. That's really what the assignment is designed for to really help you reinforce this concept over here. I'll leave that to your little bit struggle, when you do the assignment, and reach out to me for any help. Right? Just remember the tree structure here is really recursive. And we'll talk about order versus unordered tree. And we'll talk about the tree node, and this one here will be very relevant to your assignment number 3. The only difference is the children over here, rather than using array, we are using a singly linked list or singly linked node. That'll be the beginning node of the chain of the nodes. All right, so that's the difference. You want to get used to it for both flavors of the implementation. And we talk about that crazy line over here about initializing generic array. So study for that. If you want any more details, look at the recording or reach out to me. And we spoke about how you can initialize some tree structure, for example, a tree with a root and 2 child nodes. And that's the code you have to write. And when you look at the assignment, there's also one test class within the JUnit test package that's also going to show you how you can build a tree structure. So you want to look at that first before you tackle the assignment number 3. Right? That will be a very nice preparation work you can do before tackling the assignment. And we talk about how you can compute the depth over here about the some particular node. And we spoke about Java code over here. You got base case, you got recursive case, and also we talk about tracing using unfolding the recursive definition, right? That's something you want to get used to as well. When we talk about merge sort and quick sort later, we're going to need this technique as well to figure out the running time. What I didn't really go over is about the heights. And for that one there, let me just go there very quickly. And for the height here, I just found that I actually got some very nice, about 10 minutes solution video about walking through about the code and also tracing for the heights. So I'll leave that as exercise for you. So if you go to the lecture site, you will see under the tree here, you can see right here. Under exercise, I just posted last night, computing the heights recursively in Java. Right? Take a look at that video. And I would suggest you try to do the exercise over here by looking over the code about computing heights in Java and also try to do some tracing just like how we trace the depth method. And then you can look at a video if you want to. If video is more like an optional. If you want to study with me again, you can look at the video. Otherwise, looking at this page will be enough. Okay, I'll leave the exercise to you. And then we spoke about recursive definition for binary tree. That one, there's really nothing new here because binary tree is just a special case for general tree where you got at most 2 child nodes for each node, basically. Right? But the only difference is binary tree is an ordered tree. That means the child here, left child, should really come before the right child. That's very important. The order of the children is very important, binary tree. We're going to talk more about binary tree for the rest of the semester. Binary tree, binary search tree, and also balanced binary search tree, etc. Okay. And then we went over this formula here about computing the sum of the geometric sequence. Right? You can look at the formula derivation because there will not be any data sheets available during your exam or written test. So your safest bet, in case you forget about the formula, you can derive it very quickly. Right? Just remember the critical step about the rationale. I think it is a nice formula to really derive. It's not complicated. What you really want to focus on will be what I said at the end right here. The general formula will just look like this. All right? Initial term times the common factor to the power of the number of terms minus 1, r minus 1. But in the case of binary tree, which we'll see today, the common factor over here, because we know that each node can at most branch out 2 times. So that's why the common factor will just be 2, as we'll see. And the initial term is going to be just 1, because there's only a single root at the top level. So once you plug in these 2 numbers, what you will get will be something like, which I forgot to write down, but it's going to be 2 to the power of k minus 1, right? So this is the formula that we're going to use throughout today. Today is going to be a little bit more math heavy, just to show you the mathematical property, but they're very practical, not just math heavy. Right? 2 to the power of k minus 1. And the k here, as we'll see, will be typically the heights of the tree. All right, that's something we'll see today. Lots of stuff. All right. Guys, any questions so far? Okay, we are all good. So about the heights, as I said, it's a, oh, sorry, Spencer, give me one moment. For the heights, please make sure you do the exercise. It's going to be very useful for you, for your understanding. It can also help the assignment as well. And then before that, Spence, question.
Yes, so I was just looking at the heights method, and like I just wanted to ask, like, why are we using length instead of NOC?
Very good. So, okay, since Spence already mentioned, so let me just talk about just this part here very quickly. So this one here, it's more like a deliberate typo for you to actually see in some way, okay? So when you say children, the length equals 0, this one here should not be the case, right? What we should do instead will be the NOC counter. That's what you should use, all right? Good, awesome. I'm glad you mentioned. Otherwise, I thought you guys might just reach out to me and say, oh, why are you using length? Then I'll say, think about it. It's more like a logical error there, all right? NOC, very good. But you guys know the trick. All right, let's now move on to, I want to talk about just one more very simple recursive thinking on the binary tree, and then we'll talk about mathematical properties of binary tree, okay? Let's do something to warm up, okay? I got 2 algorithms over here for us. The first one is about counting the size. This one, we already did it. If you just refer back to maybe 2 lectures ago, maybe last Monday before the programming test number 1, I spoke about how you can count the number of nodes recursively on a general tree. You're going to follow just the same procedure over here. All right, for that one there, I'm going to leave empty here for you to exercise. Okay, that one there, we don't need to worry about. But I'm going to talk about the second one. All right, how do you search through the tree? All right, let's see. So let's say what we want to do is I want to define a method that goes like this. I want to define something called search. And then, of course, it's going to return a Boolean, either true or false. For example, I might say I want to search starting from A. Okay, so you can think about the A here is the root of the subtree. Well, of course, this will be the absolute root. This is the root of some subtree. So when you look at assignment number 3, always the input for your method will be just some root of some subtree. And then I want to somehow search for some item. Let's say I put in a string, right? Let's say I want to search whether or not G exists in the tree. The example here, just don't worry too much about some potential confusion. When I put the G into the crow, I really meant the data item being stored is G. On the other hand, when I say A here without a crow, I really mean like a reference to it. It's not exactly ideal, but we'll leave the precision maybe to your assignment, right? But we'll just want to get the idea. So given the root node, I want to search for this particular element, and it's going to return either true or false. In this case, it should be true. Agree? On the other hand, so this one here is going to return true. I can give you another example here. If I say I want to search from the same root A, I want to search for the value Z, let's say. And apparently you can see the letter Z is not there. So that should be returning false, right? Either true or false. Let's now consider this problem recursively. if I try to search from here, I start with the root, which is here, right? The root. And I say I want to search from here, and then I want to search for the value g, let's say. Somehow this problem here is too big for me. I cannot search the whole tree right away. I need to delegate. I need to delegate to all the child nodes. In the case of binary tree, you got at most 2 children. That's an advantage, right? You either go to the left or you go to the right. So we're going to make 2 recursive calls, basically. Either you go here or you go there, all right? So the first recursive call is actually going to actually look at the left subtree over here. And the second recursive call is going to look at a second subtree rooted at the right child. Okay, let me write it down for you. So think about this is the subtree rooted at A's left child. And here, if you look at C here, so this will be the subtree rooted at node A, which is the root right child. That's how you want to think recursively. Okay, I'm just going to write down a little bit more like a pseudocode, which I normally don't do, but I think for this example here, that's okay. All right. How should we consider that? Okay. When you want to define search, when you say I want to search from some node n, so this will be some tree node you can think about, right? And then I have some data elements that I want to search. You can think about this is some data item I want to search. There are basically 2 cases over here, right? Case number 1, base case. Base case should be if I'm already here, for example. If I'm saying I want to search for G on the subtree rooted at J, I can just return false. Because this subtree here, no way contains the G, because it only contains J. All right? So the first case will be, you want to say if n is external. And we know the definition for external, that simply means the node has no children. And then what we should really return is n dot maybe data dot equals the E. Right? So n is the input that we are talking about over here. And the E is right here. Right? And the equals may either return true or false. For example, if you get down to this particular recursive call, in that case, the item is going to be G, which is equal to the G we're looking for. Right? So that's the base case. If n is not external, that means it is internal. Otherwise, in this way, we know that n is internal. All right, I'm just going to put it here, right here. What should we write? We need 2 recursive calls. And this recursive call will be extremely similar to how we did split array, if you kind of remember, right? We say that either element will be included or not included, and we put some disjunction between them. But now here, I'm going to search either on the left subtree or right subtree. As long as the element can be found in either subtree, I should return true. If that cannot be found in either tree, I should return false, right? So here, in the recursive case, I can simply say return. Let's look for the left subtree. I can say search, calling the same method, so it's a recursive call. I can say a dot left, assuming that there's a reference there to go to the left child, right? And then I'm going to search for the same elements, E. I can also try to search for a dot right, and then for the same element over here. And then I'm not insisting that the element should really exist in both subtree. So what I can do is I can just put them in disjunction right here. So think about this call over here is really trying to handle the left subtree right here. And the second recursive call here is trying to handle the right subtree. And one exercise for you to do is to see how this recursive call starting from, for example, A, and then I want to search for G, and how is it going to be traced throughout? That's something you guys should be able to do at this point. All right, so this is the definition I want to give to you, both the base case and also the recursive case. And you have to really trace it to really see how that works at a conceptual level. And it's also going to help a lot for the assignments. Any question about this? Go ahead.
What if the node we're searching for is, let's say, the element C, where it's an internal node, but it's also the node we're searching for? Which base case, so which case would it follow?
Very good. So over here, that could be some special case you have to search, you gotta look out for. That's good, okay? So for example, you can say every time you're looking for this particular node, and even though it has 2 children, you can check for this node first, if that node actually has some the data you're looking for. If that's the case, you can return true right away. That's kind of like a missing special case, but you can put it as well. Yeah. But I'm more focusing on how you can do this left subtree and right subtree in case you haven't found it yet. Okay? Okay. Very good. Or I can just put what you just suggested. How about that? You can say another or over here. I can say the node n dot elements dot equals E. Okay, conceptually, yes, good. All right, if no question here, let's now move on. So that's about how you can recursively search for some item from the tree, binary tree specifically, okay? And then for the counting the size, I'll leave that to you as an exercise. Okay, okay, let's now talk about math, about binary tree, all right? And just don't forget, we got this particular formula from last time. I'm going to repeat it again, but just don't forget to review this page here. And let me write down here the general formula, just to remind us. So the general formula tells you if you got some geometrical sequence sk, and then it's going to be, the general one will be I times r to the k minus 1 divided by r minus 1. But in the case of binary tree, we know that we can reduce it to basically 1 times 2 to the power of k minus 1 divided by 2 times 1, which will be just 2 to the power of k minus 1. All right? So this is what we assume that we know. Okay, it's a brush up, right? I know, guys, you just get kind of exposed to this formula from last week, just from Tuesday. So you can just make sure you know that formula before written test and exam. And as we will see, the k over here, which is about the number of turns, k usually is very relevant to the heights of the tree. But we'll see exactly how. But you can make a note. K here, just about the heights, really. And we're going to build this concept from scratch very carefully. All right? So let me now try to do the following. I'm going to put more like a table. I'm going to have the tree structure. Binary tree structure, how about that? I'm going to start with a binary tree structure. Okay, so this will be one column here. And then I'm going to consider for different level. And we know that the way we divide the tree nodes into level is by their depth into the root. And the third column here will be the maximum number of nodes at that particular level. The maximum number of nodes at that particular level. We're going to look at that level by level. And just for your information, the question mark here is more to do with D, the depth. All right, we're going to look at these 3 columns, and then we're going to build out the tree very carefully from scratch. Okay, let's start with the level 0. Level 0 means the depth for the node is simply 0. We know that there's only one node, right? Just the root. So I'm just going to put a root right here. Okay, that's the root. What's the maximum number of nodes at this level? 1. All right. By the way, this is not 0. This is a node, right? This is 0. This is 1, just in case. Okay. And then let's now talk about level 1. When I talk about level 1, let's put it here. Level 1. And then how many nodes can I have in level 1? Maximum 2, right? That means the root is going to branch out exactly 2 times. The root can just branch out 1 time, but that's not the maximum. Maximum will be both the left child and right child exist. Okay? So what I will do is I'm going to write 2 nodes here. I got 1 node here. I got another node here. So that will be the maximum I can get, left child and also right child. Right? I can just say once, you can think about that's the left, that's the right. It's an order tree. Okay, level 1, and then 2 nodes, maximum. Let's do 1 more. And by the way, here you can see 1 here because both of these nodes, the depth will be just exactly 1 edge to get to the root, right? That's a very definition for depth that we said earlier. 1 more level. If I do, let's say, level 2, how many maximum? Maximum, how many? Oh, guys, it's easy, right? 4. Okay, good. You don't even bother to speak. You just say 4. Okay, sure. 1, 2, 3, 4. Okay, 1 here. That means each node is going to branch out exactly twice. 3 here and here. Okay, here and here and here and here. Okay, exactly 4. All good. And then I'm just going to make some separator over here so you can see we got level 0 and we got level 1 and we got level 2. So far, it's just about seeing some simple example. What you guys have to do as a computer scientist or engineers, you have to generalize this pattern here to see how you can generalize things. So if I give you an arbitrary level, you should really calculate the maximum number. All right? That's what we should do. We can see that so far, 1 is 2 to the power of 0. I'm pretty sure you know, right? And then 2 here is 2 to the power of 1. 4 here is 2 to the power of 2. You can see that the exponent over here corresponds to exactly the depth or the level. 0, 0, 1, 1, and 2, 2. That's the pattern you really want to observe to really let the tree grow arbitrarily deep. All right, so what I will do is I'm just going to say ... And I'm going to make things very general for you. All right? So what we should do now is to really see, first of all, the general tree. The general tree is going to look like this big, for example. Right? Like that. And then let's now consider the bottom level. The bottom level. Let's say, in this case, we got all nodes, the maximum number of nodes. So we basically got maybe node here, all the way to the nodes right here. Okay? All the way to here. By definition, height will be the maximum depth of the descendants of the root, right? So if I want to know what's the height of this particular tree, by definition, it's going to be the maximum depth of its descendants. What will be the maximum depth? One of the bottom node over here to go all the way up to the root will be the maximum depth, which will be the height of the tree. Agree? So now, how many edges are we expecting to see? In general, we just use h to say that's the height of the tree. All right? So what I would annotate the next step would be to say, okay. Let me just move this away to here. So I start from here, the root, go all the way down to the bottom here, right? I'm going to say h. What's really h? That's really important, right? H here is really the maximum depth from the bottom level. Okay, so you just gotta make sure you know where h is coming from, right? It's really based on the definition. So if you imagine that for this particular root, let's say for example, if you take this particular root, for example, let's say this one here, right? If you try to imagine you got one edge, 2, 3, all the way to 1, 2, the number of edges will be just exactly h. Right? That's how you should really imagine. All right, so that's enough about the preparation for the generalization. What we want to know is, what will be the level here? Well, actually, I already wrote it down, h, actually, right? Because the level here simply corresponds to the depth of the node. By definition, it's going to be the height of the tree, right? So the last row that we're going to have will be just h. That's the last row. And what's the maximum number of nodes at this level? Based on the pattern we just observed. 2 to the h, agree, right? Because depending on what this value is, that will be the exponent, right? That's why it is so important to observe the pattern. So that would be 2 to the power of h right here. And of course, if you want, what about the previous level? You can do that as well. Let's just do that quickly. At the previous level, over here, it will be h minus 1, which would be 2 to the power of h minus 1, and etc., right? All right, any questions so far? All right, so let's now say, so now the problem is, we want to sum up the maximum number of nodes in a tree, in a binary tree. Given that the height is h, what would that be? Well, we can use our little formula here, right? Let's now try. Let's figure out how many turns there are in the geometrical sequence, okay? So what we do is, I'll try to show you different angles. Let's say the sum, let me use a better one here. So the sum of, how about this? Okay. The maximum number of nodes in a binary tree with heights h, right? So that's the problem we are solving. Okay, let's see exactly how we can calculate this. Right, by definition, it's going to be, so let's say star here, I'm going to put it here, all right? Level 0 is going to be 2 to the power of 0, right? I'm basically summing up this particular column, right? That's what I'm doing here. Okay, I can do a little bit better. There's one here, that's what I'm doing here. Okay, I can move these two, oh, sorry. I can move these two right here. Okay, I'm summing up these numbers. 2 to the power of 0 and plus 2 to the power of 1, 2 to the power of 2, plus all the way to 2 to the power of h minus 1 plus 2 to the power of h, right? And then what I need to do is, based on the formula we said earlier, 2 to the power of k minus 1, right? 2 to the power of k minus 1. However, what's really k right here? K will be the number of turns in that sequence. How many turns? 0, 1, 2, all the way to h. h plus 1, would you agree? All right? That'll be h plus 1. All right? That's exactly what you got to do. All right, that's h plus 1. So this will be the maximum number of nodes in a binary tree, given that a height is h. Okay, and one exercise for you. What will be the maximum number of nodes from level 0 to level, let's say h minus 1, right? I just want to disregard the bottom level. All right, you should be able to visualize it and calculate that. That's an exercise for you. Yeah, let me recap very quickly, right? And then we can move on. So we kind of build this structure from scratch about binary tree. So you want to just review about the definition for level, which corresponds to the depth, And according to each depth, you got the maximum number of nodes at that particular level. And you want to sum up all the nodes together, it's going to be a geometrical sequence with the R being just 2. And also the initial term will just be 1, right? It's like a special case for the sum of the geometrical sequence. And then we got the height being h over here, and we can do all the sequence right here. You just want to know how many items are there, or how many turns are there in the sequence. It will be exactly h plus 1, right? So that's why you got h plus 1 right here. Okay. You really want to make sure you understand this formula here, because there will be some different exponent that we have to apply when we talk about different properties. All right. All right, any question about this? Yeah?
Can you just explain where the -1 comes from?
The -1? You mean the -1 here? Sure. This -1 here actually really comes from, if you look at the formula from last time. So first of all, we got this formula here, right? That -1 is really the -1 right here. All right, that's why. Nothing to do with the binary tree itself. It's just a formula for the geometrical sequence. But if you want to get from this general formula to the binary tree formula, you just got to replace the I by 1 and also R over here by 2. Okay? And K here is usually about what's the range of the levels you're talking about. Usually just H. Sometimes it could be H minus 1, which we'll see very soon. Okay. All right. Any follow-up question to this? Yeah.
Doesn't it relate to the structure? Because the root can only have one. The root is only one node, so 2h plus 1 minus 1 is just like it's just a binary tree with the first node having only 1.
Okay, put it in this way. Okay. What you can try is, you want to try trees of different sizes. That's something we can do offline, right? So this is a formula that we actually got to say, let's say h, if h is simply just 1, that means the maximum depth of the tree, maximum depth of the node is actually just 1. In that way, you're going to get 2 to the power of 1 plus 1 minus 1. That means you got 3, right? What does 3 here really mean? That means the maximum depth of the tree is actually 2. In that case, that's exactly the tree you're talking about right here, right? You want to kind of increasingly grow the value of h and see how that visualizes into the binary tree accordingly. Maybe that's how you can see the formula. Yeah. Mm-hmm. All right, let's now move on. And the next one here, let's try to apply this idea here a little bit to talk about 2 kinds of special trees. The difference is called a complete tree and versus full tree. All right, we're going to talk about them in parallel. The complete tree is actually a little bit more tricky to understand, but we'll go over the definition. Okay, complete binary tree. So given that we're given a binary tree, you want to decide whether or not a binary tree with height h is considered complete. So here's the definition. Okay, and I'm going to use an example over here to show to you about a complete binary tree. I'm going to put them in parallel. First of all, we're going to talk about complete binary tree over here. Right? Let's focus on this one just for now. For complete binary, this is one example of complete binary tree. Visually speaking, you basically got all the maximum nodes you have until the second last level. And then for the last level here at the bottom, you're basically trying to fill out the tree from left to right. That's really the visual realization about how a tree is actually complete. And here you can see E here got only 1 node. Since it's complete, the J here must be the left child. If there's a right child, then this cannot be complete because you got to fill it out at the last level from left to right. Right? Let me make that note very quickly. This one here must be the left child. Right, let's now go over definition. All right. Before that, let's now try to divide this tree a little bit here. Can you see why the height is actually 3? Because the maximum depth is 1, 2, and 3. Right? That's the maximum depth. Right? So let's try to divide them into level. So I'm just going to do, let's say here, this will be level 0. The depth is simply just 0. And this part here, depth is simply 1. And depth is equal to 2. Finally, right here, the depth is equal to 3. Right? We got 4 levels here, which is nice. And then I want to subdivide this tree over here into 3 areas. But you can also generalize it, but this example here might be nice to show you how you can do it. Let's start with the bottom level. When you look at D is equal to 3, 3 here is exactly the height of the tree. That's why it's the bottom level. So you can think about this is level H. And the previous level here, when D is equal to 2, 2 is exactly 3 minus 1, obviously. So this is level H minus 1. All right? Basically the bottom level and the last level and second last level. And the rest, all these, all the way back to the root. These will be the levels less than or equal to H minus 2. So these are the 3 areas you have to be clear to really understand the definition for a complete binary tree. All right, so we got H, the bottom level, H minus 1, the second last level. And all the rest will be any level less than or equal to H minus 2, all the way down to 0 when you get to the root. All right, and let me just say a little bit more. So you can think about over here. Let me go over definition. I think that'll be a little bit more sensible. All right, so we have done enough scaffolding. Let's now take a look at definition. Okay, part 1. To be a complete binary tree, all the nodes with depth H minus 2 has exactly 2 children. Cannot be 0, cannot be 1. Got to be exactly 2. That's exactly this area I was talking about, right? You can see for all the nodes right here, H minus 2, all these nodes have exactly 2 children, exactly 2 children, exactly 2 children. That's what part 1 definition is saying. For all the nodes with the level H less than or equal to H minus 2, they got exactly 2 children, right? That's how you see that. That's part 1. Part 2, all the nodes with depth H minus 1, which is the next one, right? That one may have 0, 1, or 2 child nodes. So that one there, part 2, is talking about this one here. When you look at H minus 1, how many children? For example, this one here has 2 children. This one here has only 1 left child. And this node here has no child, 0, 1, or 2. All right, that's part 2. Part 3. The child nodes with depth H minus 1 are filled from left to right. Okay, let's now take a look. So if you think about over here, these nodes. So if you look at these nodes, there are 2 ways to view these nodes right here, right? But they're equivalent. Either you can say these are the nodes with depth, with the depth equal to H, right? Exactly H right here. That's one way to say it because it's at the bottom level. Another way to say it would be these are the child nodes of, how about children? Children of the nodes with the depth being equal to H minus 1. For example, this node is a child node of the node at level H minus 1. And this node here is also a child node of the node with depth H minus 1. Right? That's what the definition is saying. You can go for either way. All right? All right, so what I just illustrated was about the definition for what we really mean when a binary tree is complete. Right? You really want to understand the 3 different parts of the tree based on the heights. All right? Let's now generalize it, now that we understand the example. Let's say this is some arbitrary binary tree. All right? Right here. Okay? And the height is just h. All right, the heights. And we want to figure out what's the minimum number of nodes. And also what's the maximum number of nodes right here. That's what we want to figure out. Okay? Oh, by the way, so you can think about here, what I have is, you can think about this one here is really h minus 1, and this is really h. I haven't really drawn the bottom level just yet because we need that level empty for now so we can see the different possibility. All right? What we want to know is if I tell you that a binary tree is complete, what would be the minimum number of nodes and what would be the maximum number of nodes? So what I have is I basically got the tree completely full all the way until the second last level, h minus 1. What will be the minimum in order for the tree to be complete? You just add one node. Do you see what I mean? So here, let's say I got the leftmost node at this level here. Oh, let me draw a little bit differently. I got this node here. And by definition, at h minus 1 level, those nodes should have 0, 1, or 2 children. In order to really grow to that level, I should have just one. This will be the minimum case. So I can grow to h, just plus 1. What about maximum? Maximum simply means I got all the nodes at this level here, all of them got exactly 2 children. Right? That's a maximum. All right? But in both cases, so this is the minimum, and the maximum will be if I got all the nodes filled out at the bottom level, right? Let's see how these numbers are going to vary. All right, we're going to see the pattern here. In the minimum case, I'm going to count how many nodes are there in this part, plus 1. In the case of maximum, I'm going to count also this part of the tree plus the bottom level, the maximum number of nodes, which we already learned from the previous table here. All right? I'm just going to write them down. What about this one here? If I want to sum up all the nodes from level 0 all the way to level h minus 1, right? That's what I want to do, right? That's the part. So think about this part over here is going to be, I'm just going to put, so all the way to h minus 1. All the way to h minus 1. So I'm going to write this. 2 to the power 0 plus 2 to the power 1 plus all the way to, how many nodes are there in this level here, maximum? 2 to the power of h minus 1, right? Just correspond to the depth. That's a common part. Let me write it down first. For the maximum, it will also be the same. 2 to the 0, 2 to the 1, plus all the way to 2 to the h minus 1, right? And then, in the case of the minimum, I just need to add one more node here, plus 1. In the case of the maximum, I need to make sure I got a maximum number of nodes at the bottom level with depth h. What would that be? 2 to the h, right? All right, I know it's a bit of too much information today, right? But that's something you got to know, right? That's why I kind of present that in a logical order. You want to know the formula first. You want to know that previous page about calculating maximum nodes for different levels. And now we try to apply that in different kinds of tree, right? That's the order we're going for today. All right, let's try to sum them up. This guy here, if you recall the formula, let me just remind you, as k in the case of binary tree, it will be 2 to the k minus 1, right? What's the k for here? How many turns? H, right? From 0 all the way to h minus 1. Very good, okay? So that would be basically 2 to the h minus 1. Oh, beg your pardon, 2 to the h only, right? Because it's going to be from 0 all the way to h minus 1, so just h. H corresponds to just k. And then you will say 2 to the h minus 1, and then plus 1, which will be 2 to the h. Agree? All right. So if you try to sum up these two numbers right here, it's going to give you 2 to the h. So that's the minimum. What about the maximum? Maximum, you can think about, we go from 2 to the 0 all the way to 2 to the h. How many terms? H plus 1. All right? So that one there, if you try to sum them up together, you basically got 2 to h plus 1 term. So 2 to the h plus 1 minus 1. All right? So the final answer is minimum 2 to the h. Sorry, minimum will be 2 to the h. Maximum 2 to the h plus 1 minus 1. Not too bad, huh? Yeah?
Why is the base case for the minimum and maximum of nodes? Like, why do you need the...
Yeah, so basically we are doing this. Doesn't matter if you go for the minimum case or maximum case, you must have the bottom level. The difference is really about the bottom level. But if you count the nodes all the way to the second last level, it's really the same. That's why I kind of show you the common part first. And in the minimum case, you just plus 1. In the maximum case, you just plus 2 to the h.
So, like, why do we need to, like, have at least one node in the bottom layer?
Because, okay,
If I didn't have anything at all, would that not still...
if you don't have anything at all, it's not a complete tree with a high h. Because now we're trying to visualize if you got a complete binary tree of high h, you must have some nodes at the bottom level h. So you don't really have that node, then it's like a high would be h minus 1. Then we talk about a completely different tree, right? Yeah. Good question. Yeah. Alrighty, so that's about complete binary tree. If you grasp the idea, full binary tree is very straightforward. It's basically just when the complete binary tree has all the 2 to the power h nodes in the bottom level, right? That's the definition. All right, so full binary tree, you can refer to the slides for definition. The way it's going to work is when you expand to the h over here, you have no choice. It must be filled out all the way from left to right, fully. That's why it's called full binary tree. And for both the minimum maximum, just be the same number. Okay? It's just going to be basically go all the way from 2 to the 0, 2 to the 1, plus all the way to 2 to the h, which will be 2 to the h plus 1 minus 1. So you can see this number over here just correspond to the maximum nodes for the complete binary tree. What does that mean? A complete tree, sorry, a full binary tree is a complete tree, in which case you got all the nodes available in the bottom level, right? That's one way to see it. Okay, let me do one more summary for you. Okay, you gotta digest the definition a little bit, right? You still got a week before next Thursday. Hopefully that's enough. All right, let's now summarize about complete versus full binary tree. If you talk about complete binary tree versus full binary tree, complete and also full binary tree, okay? So let's say both of them has the heights h. Right here. All right. Let's see how they're going to be different. So if I try to draw both of them, okay, one here and another one right here, all the way to h minus 1 will just be the same. So all the way to here, the bottom, all the way to here, will just be the same. And in the case of the full binary tree, you must have exactly 2 to the h nodes at the bottom level. In the case of the complete binary tree, you have some range. It can be just 1, or it could be up to full. All right, that's the difference. Apparently, that's why I said full binary tree is just a special case for a complete binary tree, when you take 2 to the h for the bottom level, right? the most important thing is for you to visualize this yourself and combine that with the definition over here. Because in the written test or the exam, I don't necessarily draw some tree to you right away, right? You have to look at the definition and get comfortable with it. That might be more or less the written description you will see in the actual test, right? So just watch out. All right, so we're done with this about complete binary tree. We're done with the full binary tree. All good. All right, let's now talk about having some lower bounds and upper bounds for the different measurement of the tree. All right, let me give you some very quick walkthrough. Okay, we got quite a bit over here. Don't worry about the equation just yet. I'm going to go over with you one by one. Okay, first of all, we're going to talk about how can we put a lower bound and upper bound for the number of nodes in the tree, which we somehow have seen that already, right? The number of nodes in the tree can be bounded somehow. The heights of the tree can also be bounded. And this usually has a very direct impact on the algorithm efficiency of your tree, because you may have to go all the way down to the bottom. So what's really exactly the height of the tree is very inferential. So we're going to bound the number of nodes. We're going to bound the number of bound the heights of the tree. And also we're going to bound the number of external nodes. What will be the minimum and maximum number of nodes without any children? And also we're going to bound the number of internal nodes as well. All right? These are the four we're going to do first. All right, let's do one by one. And the easiest way, or the most effective way to understand each one of them is by using some example there, and then we're going to generalize the pattern. Right? So that's the way to go. The first one. Let's say we're given some heights, h. Let's say h is simply equal to 3. All right? Easy enough. And then we want to know what's going to be the lower bound and upper bound for the number of nodes in that particular tree of height h. All right? And when I say h equals 3, that's the example we're using. What does that mean? That means if you imagine you have a tree right here. I'm saying that if I say h is equal to 3, what does that mean? That means the maximum depth of the descendants of the root is 3. The bottom there, to go all the way to the root, should be exactly 3, right? 1, 2, and 3 edges. That's what it really means. And now the question is, if I know that the height is equal to 3, what will be the minimum number of nodes in the tree? That would be if I only got one bottom node to go all the way to the root. I don't have any other bottom nodes to really go there. It's something called slanted tree, one way. Okay, I'll give you one example here. So let's say when h is equal to 3, in that way I know that from the bottom node, it will take 3 edges, 1, 2, and 3 edges to the root. That's a bottom node, right? You can see that's exactly 1 and 2 and 3. So at this node here, the depth is simply equal to 3. Now the question is this already a valid tree? It is. It looks ugly, but it's a valid tree. So this will be the minimum number of nodes because I don't want to add any more nodes. All right? So that's a minimum case. In general, if you actually got h, how do I visualize this kind of one-way slanted tree? Basically, you take your h edges. When I got 1, 2, and 3 edges, how many nodes do I have? 1, 2, 3, 4. Right? Because each edge will contain 2 nodes. That's why I got a +1. All right? So that tells me if I got the bottom node over here, and then I will go all the way to the root, and I know that the number of edges I have is h. The number of edges I have is the number of edges from bottom to the root is actually h. That tells me I got h plus 1 nodes. So this is how the minimum is derived. Right here. Every time you talk about a path, the number of edges plus 1 will be the number of nodes in the path, basically, right? That's a minimum. Now what about maximum? Basically, you want to think about if I got this like as a starting point, is it possible for me to add more nodes into the tree, but I'm not increasing the height or decreasing the heights? Basically, let every node in different level just grow as much as possible. Basically, I want to grow to a full binary tree, right? That will be the maximum. In the case of h equals 3, what I need to get is something like this. So I got, let's say I got stuff from here. 1, 2, and 3, right? So that's a minimum. Now I want to make sure I got 2 children for every level, for every internal nodes. So I think about this here. If you, let me just write something down here and I'll contrast for you. This is h equals 3. Because I got, for example, maximum depth is still 1, 2, and 3. Look at this tree here and look at this tree here. They have the same heights. But one has the minimum number of nodes, h plus 1. And this one here has the maximum number of nodes, which we'll get to about how many nodes there are. Right? And this one here, if you just apply the formula here, the number of nodes, in this case, the maximum will be, we say 2 to the h plus 1 minus 1. Right? So 2 to the h is 3. 3 plus 1 minus 1, which should be 15. Right? And I'm pretty sure you guys can count. I'll leave that to you. It's 15. All right? Let's generalize it. The maximum number of nodes in a tree, which we spoke about actually in that table. Right? Let's just do it again. The general case will be like this. If I got a binary tree, and then I got a height being h, right here. Right? Just h. So that means I'm going to have that completely full, all the way to the bottom level. Right? It's going to be 2 to the power 0, 2 to the power 1, all the way to 2 to the power of h. Right? I got h plus 1 term. Right? So 2 to the h plus 1 minus 1. Right? So this is where the maximum comes from. So that's the first property that you have to know about bounding the number of nodes given the heights. Let's go the opposite way. Here we're saying given the heights, we want to see what's the minimum and maximum number of nodes. What about given the number of nodes? What's going to be the minimum and maximum heights? Right? Right here. And this one is actually more fun, because somehow you will see log. You may have heard about before, whenever you talk about binary tree, you talk about log n kind of thing. This is where the log comes from. Right? That's something we got to see. Okay, again, we're going to see some example here. Let's say we got n equals 7. We got 7 nodes. Here is your challenge, right? Drawing challenge. If you can only got 7 nodes, what will be the maximum height of the tree you can draw? You just let it slant one way, right? Because you think about this. If I got first node here, of course, the only way for me to add a second node is right here. Now, thinking this way. If I want to increase the weight to the maximum, if I simply do this, I'm wasting this node because the tree is of same heights, right? But if I do this one here, I can increase by 1, and so on. That's the way to really accumulate the heights of the tree, given that you got a limited number of nodes to really draw. Right? So the maximum height over here would be something like this. You got slant tree. So maximum will be here when n is equal to 7. Okay, you got 1, 2, 3, 4, 5, 6, 7. You got 7 nodes. What will be the number of edges, by the way? 6, right? n minus 1. So the number of edges from the bottom, which is the maximum depth, will be 7 minus 1, which will be 6. All right, what about in general? In general, if you just got n, all you got to do is you're going to say here, 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 all the way to the bottom here. And if you say that I got n nodes, 1, 2, 3, 4, 5, right? Just all these, you got n nodes. How many edges would it take from the bottom node, go all the way to the root? N minus 1, right? You already saw some example there. If you got 7 nodes, for the bottom node to go there, you take 1, 2, 3, 4, 5, 6, n minus 1, right? Given 80 path, the number of edges is always 1 less than the number of nodes in the path. Okay, so the number of the heights will just be n minus 1. So this is where the maximum comes from. I want to deal with maximum first. That's maybe more intuitive for you to see. We don't need any derivation for the math right here. Okay. And let's now try with the other strategy for drawing a tree with the minimum heights. You basically don't really want to increase the height of the tree unless you have to. First node, second node. For the third node, I will just draw that as a second child if I can, so I can remain the same heights. The next node, I might do this, but what about the next node? I don't want it to go here. That's going to increase the heights. No, I want to go here, and go here, and go here, etc. Right? So the minimum height is going to happen if you try to make your binary tree as complete as possible. That's why we talk about complete binary tree. All right? So let's say we got n is equal to 7. All right? Let's now do the formula, just apply the formula first of all. Given that n is equal to 7, the minimum heights will be, let's just apply that. And as we said earlier, if I didn't really give you the base for the log, it would just be base 2. All right? Let's apply. It's going to be log 7 plus 1 and then minus 1. What's log 8? 3, right? 3 minus 1, 2. That tells me I got maximum, sorry, the minimum height should just be 2. That means the maximum depth will be 2. If I draw that accordingly, 1 and then 2. That's how I start with. And then I would simply go for here, here. I'll just make it completely full. Right? So this one here, I got the heights be equal to 2. How many nodes do I have? 1, 2, 3, 4, 5, 6, 7. Right? So formula works. Sometimes it may not be perfect number, of course. So that's why we got some inequality here, right? Okay. Let's generalize it. To generalize it, let me make this guy here a little bit smaller because I want to leave some space for some derivation. Oh, sorry. Let me put it. To generalize it, give me one moment. There we go. Okay. To generalize it, you can just think about we got some tree here. All right. You want to make it as full as possible. So that means you got H right here. And then, so H will be the minimum if the tree itself is actually full. H is minimum if the binary tree is full. Okay. And let's see how we can derive the lower bound right here. We are saying H should be larger than or equal to this log, right? Let's think about what's going to happen here. Let's start with this. If this is a full binary tree, you can look back later. In a full binary tree, we know that n is equal to exactly 2 to the power of h plus 1 minus 1. And for that one, you can check back to the earlier discussion, right? Let's start with this. If I start with n equals 2 to the h plus 1 minus 1. But I want to bound h. I want to do some rearrangement, right? First of all, I can take, let me just do step by step. this one here, first of all, I know that I can move the -1 to the left-hand side, right? So I got n plus 1 equals 2 to the h plus 1. Easy. And then I want to move the h down. How can I do that? From exponent to without the exponent. Log. All right? So I can simply say log n plus 1 equals, guys, what is log 2 to the h plus 1? What is that? For example, if I got log 2 to the 3 here, right? Okay, maybe you want to review a little bit about log. That will be just h plus 1. Okay. And that one there is just going to be h plus 1. Okay. And then I just want to get h. You can move the plus 1 to the left. So the final thing I will get will be h will just be log n plus 1 minus 1. So this is where the lower bound comes from. To really understand the lower bound, I would suggest thinking this way. When you get a minimum case for the heights, that's when you get a maximum case for the number of nodes. They kind of go side by side, right? Let me say that again. When you get a minimum heights for the binary tree, that means you got a maximum number of nodes in the tree, and vice versa. Right? Right, so we finished the first two. All right, any question? All right. I would suggest the following. I still have two more. Since I said everything I covered until today is going to be covered in a written test, I think it will be also beneficial that we talk about some tree traversal problem. And I'm going to leave the next two properties maybe until after the written test. Well, not really after. I mean next Tuesday, which will not be covering the written test. Right? Why don't we take a very short break? I want to talk about traversal. Okay, that'll be the last topic for today. Yeah, we're going to jump a little bit on the slides because I want to make sure everything I cover today is actually suitable for your written test. So I'm going to specify the exact slide range once I finish section X in the evening, so don't worry. Let's now jump to slide number 39. Okay, so it's about tree traversal, which you will also need for your assignment number 3. All right, so what's really a traversal? In the simplest intuitive sense, you basically want to visit all the nodes in a tree in a systematic way. That's really what it is, right? So these are just the common purposes for doing tree traversal. That's something you will do for the assignment, one of them, right? But let's now talk about there are 3 types of tree traversal, which I want to do in about 10 minutes, okay? So we got pre-order, in-order, and post-order. And all of them are going to be defined recursively. Let me go over with you their definition, which is incredibly simple, but I'm going to use example to help you understand, okay? That'll be the plan. We got pre-order. So here is a principle. Whenever we talk about pre-order, that means you're going to visit the parents first, and then recursively visit all the subtrees at the child nodes. Parents, and then followed by children. That's pre-order. And you will see the pseudocode or Java code here. We are going to visit the parents first, and then recursively visit the child nodes. Post-order is the opposite. You're going to visit parent the last, visit all the child nodes one by one, recursively, and then visit the parent node. That's post-order. The last one there is called in order. However, notice that for in order, we talk about precondition, right, from the ADT lecture. The precondition for in order is it has to be a binary tree. You recursively visit the left subtree, and then visit the parents, and visit the right subtree. All right. Let's now take a look. That's the definition. Let's do pre-order and post-order. We got our family tree here. Okay? At the top level, if I want to pre-order from the root, let's say as far as this root is concerned, I'm going to visit David first. So remember parents followed by the children. I'm going to visit the parents, which will be David. And then I'm going to recursively visit the child nodes one by one. So I'm going to do some pre-order on this subtree over here. So this one here is going to correspond to the pre-order of the first child, which will be Ernesto. There's only one node here, agree? So that will be base case right away. That will be just Ernesto. That one's easy. And then I'm going to recursively visit the second child of David. That one there is going to be right here. So I'm going to get some order right here. That one is going to correspond to the pre-order of the second child of David, which will be Chris. So far we have seen two nodes already, but this part here, we don't know just yet because the pre-order of the subtree rooted at Chris still has to be done. All right, let's now move on to that. How do I pre-order traversal Chris? The same definition. Visit the parent first. So I'm going to say Chris, the parents, and then I'm going to recursively pre-order traverse first child and pre-order traverse the second child. So this part here is going to be longer, as you can see, because subtree is bigger. And this will be the second child. So this will be the pre-order of Anna. That one will be just Anna. Right? What about the pre-order traversal of the subtree rooted at Elsa? That one should be, basically, we go for Elsa first. And then we have the pre-order traversal Shirley subtree, Vanessa subtree, and also Peter subtree in this particular order. In that way, each one of them, it will just be a base case, right? 1, 2, and 3. So each horizontal line I'm writing here is like a recursive call, right? So pre-order traversal of Shirley will just be Shirley, and then Vanessa, and then Peter. All right? So the ultimate order you got goes like this. For the pre-order traversal, David, Ernesto, Chris, Elsa, Shirley, Vanessa, Peter, and Anna. That's pre-order traversal. Of course, in the written test or exam, you don't need to do this kind of different layers of recursive call. Once you get quick, you'll be better. Okay, post order. The opposite way. If I want to do post order on this tree, the same tree here, David, unfortunately, will be visited last. Right? So that means I'm going to do Ernesto post order. Post order of Ernesto, which will be just Ernesto. It's a base case. And then I'm going to do post order of Chris, which is going to be something big. I'll put it here. And then that will be the post order of Chris. And for the parents, which is going to be David, is going to be the last. Sounds so good, right? Now, how do we do the post order for Chris? Well, Chris is now the root of this particular subtree. Chris should go last, right? So what I will do is I'm going to put Chris last. And then I'm going to do post order on the first child of Chris, which will be Elsa right here. So it's going to be something like here. It's going to be the post order of the first child of Chris, which will be Elsa, which I'll get to in a moment. And then I should also try to get the post order of the second child of Chris, which will be Anna. That'll be the post order of Anna. And that will be base case Anna. All right? Guys, help me out. What would be the post order for this subtree here? First one? Shirley, Vanessa, Peter, Elsa. Okay? Okay. All right, so for that one there, you're just going to get Elsa will come last, the parents. And then you go for Shirley, you go for Vanessa, and then you go for Peter. Okay, each one of them will be the base case recursive call. You got Shirley, you got Vanessa, you got Peter. All right, so ultimately, this is what you get. You got Ernesto, Shirley, Vanessa, Peter, Elsa, Anna, Chris, and David. Of course, it's different. And don't think pre-order just a reverse or post-order. No, it's not that simple. All right, in case you're thinking that way, no. Okay, now in the final 2 minutes, I'll give you guys think about this particular tree here, right? It's more like an arithmetic tree, the same tree. Okay, and then let's now go over this. This one I can leave there is exercise for you before Tuesday, but that will be covered as well. But I can just go over solution with you right away. Right? Let me do it right away, and then I will give you some idea about how you can understand the linear order that you get. Okay, pre-order. Minus, divide, multiply. Oh, sorry, let me do it again. Minus, divide, multiply, plus 3, 1, 3, plus, minus, 9, 5, 2, plus, multiply, 3, minus, 7, 4, 6. Pre-order. One way to see that, think about this guy here, corresponding to this. And this guy here, all the way to over here, is the pre-order for this subtree over here. You can verify. And this one here is the pre-order for this particular subtree. And you can move on as well. Okay, that's the first one. Pre-order. Post-order. 3, 1 plus 3 multiply 9, 5 minus 2 plus divide, and then 3 minus 7. Oh, let me do it again. Sorry. I got distracted myself. Not your problem. My problem. Let me do it once more. Maybe you can do faster than me, right, in the written test. I'm pretty sure. 3, 1 plus 3 multiply. 9, 5. Okay, sorry about that. 9, 5 minus 2 plus divide. I'm done with the left subtree. And then 3, 7, 4 minus multiply. 6 plus minus. Okay? So you can think about minus is really this guy over here. And then this is the subtree for the left that go all the way to divide right here. And then we got this subtree over here. You got to practice on this. Okay, I'll leave the in order traversal for you, and then we'll go over once more on Tuesday. But you got to make sure you study up to here. Look at the recursive algorithm and try to practice this. All right, I'll see you next week.